So, in the previous class we have learnt Young's double slit experiment, where division of wavefront was employed to produce the interference pattern. There are other techniques like FRENSNEL'S biprism. We will see how in FRENSNEL'S biprism method the division of wavefront is employed to produce interference pattern. So, in FRENSNEL'S biprism, a thin prism is taken, thin prism with this angle of prism, very small angle, this angle is A, this is also A, this angle is very small, of the order of 1 degree, 1 by 2 degree, 1 by 3 degree, like that. So, in this experiment we take a source S, point source, and the two halves of the biprism is used to produce two virtual images. So, you see here a ray, this ray, so this is the biprism, and you see that here this is the point source and the wavefronts here, this is the primary wavefront, this is the wavefront, spherical wavefront, and this wavefront refracts from the upper portion of the prism to form a virtual image S1. This virtual image of S as S1 acts as one slit, and the waves refracted from the lower half forms a virtual image S2, and these two wavefronts interfere. You see, this is the wavefront, this is the wavefront that seems to be coming out from S1. This is the wavefront, you see this wavefront seems to be coming out from S1, and there is a wavefront from the lower half which seems to be coming out from S2. So, this wavefront seems to. So, this is the region where the two wavefronts superimpose and form an interference pattern. So, this is the region where interference pattern is formed. We wish to calculate what is the fringe width here and how many fringes are there. So, the basic idea is that this is the biprism. This biprism has a very small angle. This is the source. The source emanates a spherical wavefront. The upper half and the lower half divide the wavefronts into two parts, which seems to be coming from S1 source and S2 source, and these two wavefronts are allowed to interfere on the screen at a large distance, and thus interference pattern is formed. This is the FRENSNEL'S biprism method. So, now we will see that what things are required to calculate. Let this distance be A and let this distance be B. So, we will see that how first we will calculate what is this slit width d. This is our general terminology is d. In this experiment, the slit width will be d and the distance between the slit and the source will be a plus b. Now let us calculate it. Now this is my Fresnel's experiment. This is the biprism, this is the source S1. So now the wave front that is refracted, that is suppose A1 B1, this is the region A1 B1 is the region illuminated by the upper wave front, and A2 B2 is the region illuminated by the wave front from S2. These are virtual sources. So this is the region where we are going to have the interference pattern. So first let us calculate what is the slit width the S1 S2, the distance between the slits. So we will use the idea that if we have a prism and this is a point source, then array will get deviated by deviation equal to a mu minus 1. This is the deviation formula by a thin prism. So you see, if I produce this, I get the first image S1. So this is deviation, this is A. So this angle of deviation is small. So S1 by A, S1 by A gives tan deviation, that is deviation, that is A into mu minus 1, implies S1 is A mu minus 1. Now the slit width is S1 S2, that is 2 times S1, that becomes 2AA into mu minus 1. So we got this slit width. We will write it here, that slit width S1 is equal to 2AA mu minus 1. Now you may think that why the image is formed here, why not here and why not here. So you see the deviation produced by a thin prism does not depend for the angle of incidence if it is near normal incidence. For thin prism and near normal incidence, deviation does not. So if you take other ray, it will also meet at here only. Okay. So now we have calculated S1 S2. So this is over. Now the fringe width beta is given by lambda d by d, where lambda is the distance between source and this, and here this distance is given as A and this distance is given as B. So A plus B by S1 S2, that already we have calculated as 2AA mu minus 1. So this is the fringe width beta in our biprism. Now how many number of fringes will be there, we can calculate by seeing this triangle S1 S2, this let us call it O, and this triangle OB1 A2. By similarity of these two triangles, let us draw these two triangles S1 S2, and you see it's something B1 and A2, and this is O. So this is the region where we are getting interference pattern. We know the fringe width beta, how many number of fringes are there. So we can say that these two angles are equal, and this angle is equal to this is equal to this, because they are parallel. So these two triangles are similar. So for similar triangles, A2 B1 by S1 S2, this by this is equal to this by this, that is B by A. So A2 B1 is equal to B by A S1 S2, and S1 S2 is here 2A A by mu minus 1, that is A cancels out, 2BA mu minus 1. This is what? A2 B1. Now we got A2 B1 and we got beta. So now I can calculate that how many fringes are there. So how many fringes are there means number of fringes n will be given by A2 B1 by fringe width beta. Beta is A2 B1 is 2BA mu minus 1, and beta already we have calculated is lambda A plus B by 2AA mu minus 1. So this 2 becomes 4AB A square mu minus 1 whole square by lambda A plus B. So now we have mathematically calculated the total number of fringes available here. This is the region where fringes are formed, and what is beta. So this is what Fresnel's biprism is.